All right, good morning. This is the third class of Mime 3380. And if you're interested, we can start by looking at the quiz that you took yesterday. So the main step for both of these systems was to arrive at a differential equation. And we are working with first order systems, and you know the standard form of a first order differential equation is what is shown here. So this is the standard form right here. Tx dot plus x is equal to a constant times the input, where x is the output of the system and the only state variable. The system is first order, and therefore it has one state variable. So our goal is to start from looking at each of the circuits and arrive at an equation that looks like that. So if you look at the first system, what I've highlighted as number one, this is a source of voltage in series with a resistance and an inductor or inductance. And following Kirchhoff's voltage law, this is a closed circuit. You go around the circuit and add up voltages. Source of voltage obviously is a positive voltage. As you see, I'm talking about equation number one. So V minus I times R, which is voltage drop across the resistor, minus L di over dt equals to 0. That's Kirchhoff's law. So you go around the circuit, you add up voltages, and that's equal to 0. And you can immediately see that the only variable that is differentiated is what variable in equation number one? I. So it makes sense for I to be our state variable. The whole purpose of the model is to capture how the state variable changes over time. So you can see I is the output. We normally use variable y to show the output. So I is the output. What causes this output to change is the input, which in this case, again, makes sense to be the voltage. It's a first order. The only state variable is the current, and the output is the current, and the input is V. Now let's look at any questions so far on the first problem. So let's look at the second problem. The second problem, we have two of these elements with the source of voltage all in parallel. So we have voltage, we have resistors, the resistor, and we have the inductor all in parallel. So if there is the source of voltage applies a voltage V, and a current I passes through that main connector. And that current is split into two portions, I1 and I2, and we don't know what the value of each of those portions are. So I1 and I2 are unknown. But what we do know is that the total voltage is equal to I1 plus I2. And why do we know that? Because we have this node here, and according to Kirchhoff's law and conservation of electric charge, current coming into a node is equal to current leaving the node. So I has to be equal to I1 plus I2. Now, what is I1? What is the current passing through this section? Now, source of voltage is in parallel to both of these. So it means the voltage applied at each of these two elements is equal to V. So the current passing through this first element is its voltage divided by its resistance, V over R. And the current passing through the inductance element comes from the basic equation of the inductance. If you remember the basic equation of the inductance, I can write it up here. For an element L, the basic equation is V is equal to L di over dt. That's the basic equation. Now, what we are trying to find is the current, which means we have to take the basic equation and do what to it? Integrate it. So you need to integrate it. If you integrate this equation, what you have is, what you get out of integration is what? Let me see if I can move this. just write it here. So what I can get as a result of integration is that I is 1 over L integral of v dt. And that is exactly the equation we are using here in here. So the total current is V over R plus 1 over L integral of V dt. So the next step for this equation to bring it into a form of a differential equation is to get rid of that integral portion. So you integrate this equation and you have di over dt equals to 1 over R time differential of voltage. This is from the first portion of the right hand side. And the second portion, basically the integral disappears. So the form of the equation is di over dt equals 1 over R dv over dt plus 1 over LV. Now, based on the prior information that you have, you know that the state variable in a typical first order model, the state variables time differential as well as the state variable both show up in the model. And if you look here, that is the case for voltage. Both voltage and its time derivative appear in our differential equation. So that's an indication that your state variable is voltage and so is your output. And your input, you can call it either. You can consider the current to be your input, or to keep it simple, so you don't have to differentiate your input, you can call di over dt, time derivative of current, as the input to this system. Now with that choice, we can rewrite both the first differential equation as well as the second differential equation into the standard form. What is the standard form? The standard form is when the coefficient of the state variable is equal to 1, as we covered last time. So we want to arrive at the format when you have a constant multiplied by x dot. By now we know that constant is the time constant of the system. And the coefficient of x should be 1 and another constant multiplied by u. So the first equation, which is what we have up here, the red equation, it's fairly easy to take into that format. You simply rewrite it and take the state variable and its time derivative to one side and make the coefficient of the state variable equal to 1. So if you push these two terms to one side and keep v on the other side and divide through by the coefficient of I, you get L over R rather di over dt plus I equals 1 over RV. And from here, you can immediately see that the time constant is equal to what for this system? L over R. So the time constant is L over R. So you can do the same thing to the second differential equation that we found, making coefficient of V this time be equal to 1, as V is our state variable. So L over R again becomes our time constant, and on the right hand side you have L times di over dt, which we decided is going to be our input. Now the other part of the equation asks you, if the input is a constant, find the steady state value of the output. So for the first equation, we decided that the input was voltage. So the question basically becomes, if voltage of 1 is applied to this circuit, what would be the steady state value of current? So you set V equals to 0. And how do you find the steady state value of a variable when you have a differential equation capturing its change? What is the method? Again, I'm waiting for you to tell me. So how do you find steady state value? So you have a differential equation like what you have here in any of these two cases. In case number 1, our question is, if V is 1, what is steady state value of I? So my question is, where do you start? What do you do next? Yes. That is the definition of when the system is in steady state. That means its output is no longer a time variable, it's constant. So to capture that, you let any term that has a time derivative equal to zero. So you set di over dt equal to zero, which will give you I steady state is equal to 1 over r times v. Now you know v is 1, so that tells you immediately that I steady state is 1 over r. So the amount of resistance, the value of resistance, basically defines the steady state value of current. Now from the second equation, again the same condition. We are saying the input, which is in this case di over dt. We discussed and decided di over dt is our input. So if that is equal to 1, what is steady state value of the voltage? You do the same thing. You go to the right hand side and say the voltage at steady state no longer changes. Then V steady state is going to be equal to L because di over dt has a value. So if you look at both of these equations on the left, the time constant for both of them is L over R, which is the coefficient of first time derivative of the state variable. If you look at the equation for a tank, I wanted for you to take a look to see the analogy, the similarity. So if you compare the left side of a tank equation to the left side of either of these two equations, you can see the cross-section area of the tank is similar to the inductance, and R. Did I mix these things up or no? Yes, I did. So let me correct that. So from the tank side, we have two variables. So A from the tank side is similar to the inductance on the circuit side, and C, the coefficient of orifice, is similar to resistance on the circuit side. That was pretty much it. I also asked you to plot the response. The response basically is a typical first order response, such as what we saw here. So this is the typical response. So for the first circuit, this is the typical current response. The second system, this is the typical voltage response. So when time reaches time constant, the system has reached 63% of its steady state value, whatever that value is, and the response is this exponential rise, which then settles at the steady state value. How do we know that? Because this is a first order system, we have managed to take the equation into a standard form. So everything that we learn about any of these first order systems apply to any other first order systems. And that's one of our goals here, to find general trends and take it from one domain and apply it to the other domain, and feel comfortable generally manipulating differential equations and getting information out of differential equations. Any question you might have? Yes, sir.
On the second one,
Mm-hmm.
so if you use the voltage law setup, so you had two loops,
Mm-hmm.
you added the two loops together.
Okay, what will you get? Did you try that one? Was your equation different?
Yeah, it was a lot different.
Okay, so would you like to share it with us so we can look at it and see if that essentially the model is different?
Yeah.
Okay, I'll add a blank page here and we can take that. Your solution. So we are talking about the second system, right?
Yeah.
So let me draw it here and you can come up here and share what you have here. So we have a source of voltage, and then we have a resistance, and then we have an inductance, right?
Yeah.
So let me draw. Okay, so this is L, this is R, and this is V. So you're saying, could you tell me how you solved it, and I can try to replicate it here? So you said there are two loops here.
Yeah.
Okay, the first loop gives you what?
The first loop is V minus R.
So loop, should we call it loop 1? V minus,
R.
what did you call the current passing through the R?
I1 minus I2.
Okay, so you called, did you call this current I1 here?
The loop current I called I1.
The loop, which loop? Number 1?
Yeah.
Okay, but that loop doesn't have a single current. Can you see that? In the first portion of it, there is current that comes from the source of voltage, but that current is split. So I agree that there are two currents, but we need to name them so we can defend our decision. So if you call the current coming out of the source of voltage I1 and the current going through the second portion I2, then what goes through the middle one is I1 minus I2. Should we stick with that, or I want to follow your solution so we don't have to reinvent the wheel per se? So should we do that?
Yeah.
Okay, so if we call the current in this section I1 and current in this section I2, then what you have is minus R times I1 minus I2 for loop 1 is 0. Did I capture your solution correctly?
Yeah.
Okay, then we go to where?
Current through L.
So we consider this big loop or this loop? Which loop?
That small loop.
The small loop here.
Yeah.
Okay, that's what you call loop 2. Tell me what is the equation there? You have L what?
L times di2 over dt.
Mm-hmm. That is the voltage drop there. Okay. And then you include R.
Yeah.
Okay. So how will R appear?
Plus R I1 minus I2.
So I1 minus I2. And this is plus?
Yeah.
Is this negative or plus?
That's negative.
So this is negative, this is positive.
Yeah.
Okay. So what else did you do? So I agree. These are the two loop equations that we can write. What else? What did you do next?
And then I set that equal to 0.
Of course, this is a loop, yeah. So Kirchhoff's law says it has to be equal to 0, yeah.
And then I added the two equations.
Okay, so if you add the two equations, what will you get? So the plus and minus R will cancel each other, right? So you get V minus L d I2 over dt equals 0.
And then that's the equation I used.
Okay, and that equation is correct. However, what this models is the effect of voltage to a portion of current that passes through a portion of circuit. If that is the purpose of modeling, you got your model. So again, as long as we do the steps correctly, there is no right model or wrong model. What defines or what chooses the model is our purpose of modeling. What is it that we want to model? If you go back to the two models that we developed, we tried to capture a more global behavior. So we tried to capture the effect of the main voltage and main current on each other. So that's what we did. And what helped, again, it modeling like anything else takes a lot of practice. So it's not that, okay, you write and say, boom, this is my solution. What helped when I was solving this problem, especially for the second one, which is less obvious than the first one, was I knew what format I wanted to take my model to. I knew that I needed to have an x dot, I needed to have an x, and I needed to have an output. So these were the three elements that I was trying to bring to your model. And by the way, I thought about your approach of modeling, but it didn't bring everything together. So I said, okay, what will bring everything together? and it appeared that I need to go by the node and write the. And thank you for the question. Anything else? Any other difficulty or insight you got by doing the quiz? Okay, so why do we do quizzes? To give you an incentive to stay on top of everything. So please look at it this way. Of course, there are shortcuts, but the shortcuts in the long run would hurt you. And the typical quizzes that have been given in the past happens over a specific 1 hour of the 24-hour, but I wanted for you guys to have flexibility. I realize people work, you have other commitments, especially people who are away doing a co-op. So I'm going to give you 12 hours, typical 12 hours, and you have 1 hour to do your quiz any over the 12 hours. Now, I timed myself and it took like 10, 15 minutes, and I give you 3, 4 times as much. So please do send me your feedback. If you don't want to speak up here, do send me email, or also people who are on the online section, do give me feedback. What is working for you? I've already received a few feedback emails, and I've written back to folks. So if something is working or not working, I appreciate letting me know. Should we move on? Okay, so this would be part of the annotated notes. You will have access to this solution. So we looked at an alternative way of modeling. Now it's time to upgrade. So far everything that we said resulted, or every example that it investigated resulted in a first order differential equation. In other words, every system that we modeled was a first order system. Now we want to look at higher order systems. And where do we go from 1? We go to 2. So we are going to look at a few second order systems and maybe higher orders if you get 2. So what differentiates or identifies a second order system? The typical. What made a system first order? It had one state variable. So if you're dealing with a second order systems, how many state variables are there? 2. And the differential equation that you would get in the first order system, the differential equation, the highest order of time derivative was 1. In a second order differential equation, in the second order system, its differential equation, the highest time derivative would be of order 2. So that's what differentiates a second order. So let's look at an example. And this example is made of 2 familiar systems. So we have a tank like before. It has a feed at the top. We call it WN. Surface area is A1. There is an orifice with constant C1 at the bottom of the first tank. But what goes out of the first tank enters a second tank. So we have a cascade here. What physically leaves the first tank enters the second tank. And the second tank has a similar structure, of course, a different cross-section area, a different orifice that defines how much fluid leaves the second tank and goes out of the system. By the way, this is a system. So what we call our system, what we want to model is this entire behavior. So we are interested in capturing behavior of the entire system. So I'm going to give you like 30 seconds. Try to write the equations that would govern the system. And then I'll show you my solution. Or we'll work together on it. should we pause for a second and think about the purpose of modeling? What should the model do for you? Again, that is very, very important to recognize from the beginning. When we had a single tank, what was the purpose of modeling? What information did we need? We wanted to follow what? Get what behavior out of our model?
The water level.
Exactly. So we had one interest, and that interest was we wanted to know what water level was for that single tank. So when we are talking about two tanks, what is our goal? What do we want to know at all times? Probably both water levels. So H1 and H2 are what then? Are our state variables, and they could be both our outputs. Now the system has two outputs. Now, again, the purpose defines everything. You could say, I really don't care about H1. As long as I know H2, I'm satisfied. Then in that scenario, with that purpose, only H2 would be your output. If you remember, we said output is either the state variable or a subset of state variables. In this case, we have two state variables. In this case, we have two state variables, and depending on the purpose of modeling, either the output would be both or one of these two state variables. So what did we say? We said, so a state, because now we have two state variables, we have to distinguish it from a case where we had only one variable. So the notation we are going to use is still x, but to distinguish it from a single variable, a scalar, we will use an underline to say that this is a vector, and we are going to use a vector notation and capture both h1 and h2. So this is a vector. It has two members. It's not a single number. There are two numbers that constitute our state, and this is a state vector as opposed to a state variable. So we have two state variables, and x is a state vector. So x is a state vector. Now, how about input? What is the input to this system? The first flow. What causes the entire thing to start moving and changing is the first flow. So it's Wn is our input. So we reserve U for highlighting the input. For the variable U is for input. So we said there are multiple possibilities for output. So for example, one of the possibilities for output, we call it Y1, could be that we are interested only in the level of the first tank. That would be one output. Another possibility for output is H2. And can you tell me the third possibility for the output? So how can I capture that? So Y3 is equal to what? Them added? That's a very interesting suggestion. Let's think about that for a second. So if our output is H1 and H2 added, and you are looking at this system and you have a monitor, and this is a digital display, and the way it gives you these two outputs is we have a sensor on first tank and another sensor on the second tank, and it combines the number into one and gives you that display. So it says tank 1 plus tank 2 has this much water in them. And it's very useful information because you can get collectively how much water we have. But if the purpose is to control the level of these tanks, if you don't want any of them to overflow or any of them to be empty, then that combined number doesn't give you enough information. Can you see that? So it could be that you get one number but describes many different possibilities. So the number could be 10 gallons, but it could be 10 gallons all in one tank, or distributed 1, 9, 2, 8. You see where I'm going with that? State variables, this is a very excellent example or answer that he gave. State variables should give you a complete picture of what is happening in the system with no ambiguity. So if you see the state variables, you should immediately see what is happening. So do you see what problem we'll have if we add H1 to H2? If we see that number, we don't really know which tank has how much. So what is another option? To still know H1 and H2, but not combine them. Could Y also be a vector? How a vector is different than a scalar? A vector has multiple elements in it, and it's a two-dimensional vector. It has two elements in it. So both Y and state variables are vectors. So they're not single elements, and the reason is we are dealing with a higher order system. We are no longer dealing with a single order, first order system. So that's why we are now upgrading and we are going to use vectors. Okay, so I'm ready for your equations. Tell me when you have them. So what is the first equation that you can write? So cheat. Look at your notes. Tell me something. What I don't want is silence. Don't look at me like I'm from another planet and you don't know what I'm talking about. So tell me. Yes?
For the first tank, we just do what we did before. We have H dot equals 1 over A times Wn minus CH.
Absolutely. So the basic equation was, from the beginning, it was A1 H1 dot, right? Plus what? Was it plus CH1? Plus C1H1 was equal to Wn. Is that right? Could you double check? Yes? Okay, so that's the equation that we can write for the first tank. Did you see that? So that tells us how the first tank behaviors, as if the second tank doesn't exist at all. It just captures the behavior of the first tank. Now let's go to the second tank. What can we write there? Just following this example that we have at the top. What can we write? Yes?
Could we just do the same thing except just switch everything to the second tank variable? So like
A2, H2 dot. That is change of volume in the first tank. Change of volume in the first tank is equal to flow coming in minus flow going out. Now, what is flow coming into the first tank? What flow comes to the first tank? I'm sorry. Let me rephrase my question. What flow comes to the second tank? Because we are modeling the second tank. What is the flow coming to the second tank? Which is what? What is the flow out of the first tank? Absolutely. So it's C1, H1, and it has a, remember, note that this has a positive sign because this is inflow to the second tank. What goes out of the second tank, which will have a negative sign? C2H2. Exactly. So C2H2 is how much fluid goes out of the second tank. So the concept is the same. We are saying change of volume, which is A2 times H2 dot, is equal to volumetric flow coming in minus volumetric flow going out, which is exactly how we applied to the first tank. We said change of volume in the first tank is volumetric flow coming in minus volumetric flow going out. In the first tank, flow coming in was Wn, flow going out was C1H1. Now C1H1, when we wrote the equation, was on this side with a negative sign, but when we rewrote it to give it the appearance of the standard form, it went to the other side. So we can do the same thing to the second equation and rewrite it. So this becomes A2 H2 dot plus C2 H2 is going to C1 being equal to C1 H1. So we have two equations. And we can, now this is a second order system. You already mentioned that. And one way to see it is we have one first order differential equation that captures the change in the first state variable, h1, and we have a second first order differential equation that captures the change in the second state variable, h2. So we can do that, and we can, by the way, analyze many different things with the same equations. For example, let's do this. Let's say, just as an example, if Wn is 1, what is the steady state value of h1 and what is the steady state value of h2? Can you calculate that? So find h1 steady state and h2 steady state. So that's our question. So we want to know h1 steady state. What is it? Also, we want to know what h2 steady state is. So take some time and calculate those. So what is the method for calculating h1 steady state? You look at equation 1 or equation 2. If you look at equation 1, so if you look at equation 1 and set h1 dot equals 0, that's the essence of h1 steady state. h1 doesn't change, so h1 dot is 0. So if you set that and we know Wn is 1, what do you find for value of h1? As 1 over? So 1 over c1. That is the value for steady state level of the first tank. Now, how about this steady state level of the second tank? How do you find it? You go now to the second equation that captures the change in H2. You set what equal to 0? You set it equal to 0, H2 dot equal to 0. So the equation you get as a result is that C2H2 steady state is equal to C1H1 also in steady state. Okay, so what is that value? We already know what H1 steady state is. So it is, so we have the C1 and we know H1 steady state is 1 over C1. So we can find H2 steady state as equal to 1 over C2. Okay, the next question could be, what is the time constant of each of these two tanks? Can you find them? In order to find the time constant, you need to create the standard form. In order to, the standard form, if you recall, is Tx dot plus x is equal to a constant multiplied, or u divided by a number, or equal, the same way you could say u multiplied by a number. So what is time constant of the first tank? Just by looking at the differential equation. Did you say A1 over C1? That's the time constant of the first tank. What is the time constant of the second tank? This basically tells you how quickly H2 changes. Now, the first time constant told you how quickly H1 changed, because if you look at the first differential equation, that is what it captures, how H1 changes with time. The second equation captures how H2 changes with time. So the time constant that we find also tells you how quickly H2 changes. So T2, if you look at the equation, is going to be equal to A2 divided by C2. Now, depending on the numbers, numerical values for A1, A2, C1, and C2, you can basically calculate exact numbers for speed of the system or where the two tanks will settle if you give it a specific input. Now, a quick challenge for you. What if Wn is equal to 2? Do you know what H1 steady state and H2 steady state would be immediately without doing any calculations? What is H1 steady state? Yeah, it's 2 over C1. 2 over C1, and H2 steady state is 2 over C2. Why? What is the fundamental reason? It starts with the letter L. Because we are dealing with a linear system. So in a linear system, double the input, output gets doubled. So if you double the input, H1 steady state becomes 2 over C1, and H2 steady state becomes 2 over C2. We are dealing with a linear system. So this is a time invariant linear system. What makes it time invariant? Something should not change with time. We know that. But what is not changing with time? Why do we call this system time invariant? Look at the equation, any of these two equations. What is not changing with time? Therefore, this system is time invariant. Or maybe if it is changing with time, then we have a time variant system. But let's just make that assumption first and see if we can justify why this system is time invariant. Yes? So you're saying Wn is not changing? That's only one condition, but input could change. We are just looking at one example. But even in that example, once it's 1, the other times it's 2. So it's possible that it changes. Yes?
Because the input doesn't affect the time constant?
So you're saying it doesn't really matter how much input you put into the system. The behavior, the speed of the system is not affected by the value of input, but it's affected by the time constant. You're right. But that's not why we call the system time invariant. Time invariant means that the physical system itself doesn't change over time. So A and C, A1, C1, A2, C2, they don't change with time. That's why this system is called time invariant. Do you remember the example of the car that I gave you? I said, if mass of the car and the drag force, the drag coefficients, they don't change, that's a time invariant system. But in reality, mass does change, so that assumption is limited in validity. So this system is linear because its differential equation is linear. It's time invariant because A1 and C1, the parameters that defines the physics of the system, they're not changing with time. That's why this is a linear time invariant system. So here's your challenge. It's a slightly different appearance of a tank, but you have all the tools to model this tank. So I'll give you a couple of minutes to go ahead and model this tank. To give you a little bit of tool. So when you see an orifice that is at point A, to distinguish it, you can simply say this is C of A. Or for this, you can say this is C of C, to just distinguish that this orifice may have a different opening than the other one. That could be a valve that you have opened or you can close at some point. So what is this? This could be a chemical reactor. You're trying to process and separate certain molecules, so you have to maintain a certain level of fluids, a certain pressure, certain temperature. Here we are focusing on keeping the level of fluid at certain. And what you see here as orifices, as I said, these could be valves. So you can open valve A, you can close valve B, you can open valve C at different points. So you need a model to predict under various conditions what will happen to the level of fluid so you can control it, so your system can function. You can separate the molecules you want, you can do the refinery or what other function that you're trying to achieve. So should we start? What is the first equation that we can write for the first tank? To just give you a bit more information, you need the cross-section area of this tank. So call it A1 and this A2. So what can you write for the first tank? Should we start by writing A1 H1 dot? That is the change of volume. Okay, so that is equal to what? Volumetric flow coming in minus volumetric flow going out. What is the flow coming in? Which is what comes through the pump. So let's call it Wn. Is it okay? Okay, so let's call it Wn, recognizing that's the flow of the pump. So we can go here and call this W in. That's what we call W in. Okay, so what goes out? Anything? Which C are saying CA?
Yeah, CA.
Okay. So you're focusing on what fluid leaves the tank here, right? At point A. So you have CA as the constant. Now we need to look at how much fluid is above that orifice. How much fluid is above that orifice? Yeah, the net fluid above that orifice is H1 minus Now, please note that H3 is a constant. H3 is not a variable. H3 just shows the distance of that orifice from the bottom. Can you see that? H1 is a variable, and very much so, it's a state variable. It's the level of the first tank. But H3 is just a constant. Okay? All right. So we capture that. Is there anything else that we need to write into this equation? Yes.
We need to account for the orifice B.
At point B, yes, I agree.
Bottom.
Yes, yes, yes. And how should we capture that?
Would you subtract
Mm-hmm.
then C of B?
Subtract C of B. What is the fluid above C of B?
Would it you just multiply by H1?
H1, yeah, H1 definitely plays a role. But let's just entertain this scenario for a second. If the level of the first tank, which is shown by H1, is equal to level of second tank, which is H2, would there be any flow through orifice B? If the two tanks are exactly at the same level? If H1 is equal to H2, remember H2 is the level of the second tank.
If you so that second tank,
Mm-hmm.
you have the orifice C of C.
Mm-hmm.
I guess just playing around with it. If you were to seal that off, then no, you wouldn't have any movement. But since that's open, you do have movement. Which
Okay.
kind of confuses me.
Yes, yes. So let's just seal that off for now.
Okay.
So existence of C at C or C orifice at point C is not going to affect how the first tank is changing. Not very directly. I know having an orifice at C affects the level of the second tank, but for now let's seal it off. Let's assume it's not there. Okay. Now imagine this scenario that H1 and H2 are equal. Would there be any flow through B? Probably not. Can you see that? The pressure on both sides are equal, so there is no reason for fluid to go anywhere, right? Now entertain this possibility that H2 is more than H1. Would there be any fluid going through orifice B? Yes? In what direction? Back to the first thing. So my suggestion, I'm going to write it down and you critique me. My suggestion is to capture the fluid that is leaving the first tank as H1 minus H2. So CB times H1 minus H2, and I'm open to your critique. So what this says is, if H1 is more than H2, there would be fluid leaving the first tank, and therefore it's negative. If H2 is, however, more than H1, the content of that parentheses would be negative, multiplied by the first negative, that becomes positive, which tells you that fluid is coming to the first tank. Remember, this equation captures the behavior of the first tank. We are not yet capturing what happens in the second tank. Do you see that? Do you agree with what I have, or should we make any corrections? So we are looking, so this equation captures all of the possibilities. If H1 and H2 are equal, what will happen? That becomes 0. So no fluid going out, no fluid coming in. If H1 is more, it captures the fact that fluid will leave the first tank. If H2 is more, it captures the possibility that fluid comes to the first tank. So it captures, and that's how a model should be. It shouldn't be dependent on whether or not H1 is more than H2. It should capture all possibilities. Okay? So what am I missing? Anything? Okay, so that's tank 1. Okay, should we move to tank 2? So A2 H2 dot equals what? So we need to capture to put what comes into the second tank as positive and what goes out of the second tank as negative. So what comes into the second tank? There is the input from Ca. So how should I write it? Exactly as I have on the top, only with positive sign. That's the flow going through the first orifice. This is now an input to the second tank, so it appears with a positive sign. Focus on CB. Now CB, exactly the same appearance, only with positive, plus CB, exactly H1 minus H2. Now let's pause here and think for a second. If H1 is more than H2, that tells me that fluid is coming to the second tank, therefore it's positive. If H2 is more than H1, that becomes negative, which captures the fact that fluid will be leaving the second tank. So it captures both possibilities. And if they're equal, nothing happens, if H1 is equal to H2. So these are the two fluids that come into the second tank. Is there anything that leaves the second tank? So minus C at point C multiplied by what?
H2.
By H2. Multiplied by H2. So did we capture every possibility here? Yes, sir.
For the CA times H1 minus H3 part,
Mm-hmm.
it makes sense when H1 is greater than H3.
Mm-hmm.
If with the situation where H1 is less than H3, that there wouldn't be any flow through CA, but we're showing that there would be.
Absolutely. So we need to capture that. So we need to capture the possibility. So the only time that there would be fluid leaving the first tank is if H1 is more than H3. If it is less than that, if H1 is less than H3, what will be the condition? What will happen?
There wouldn't be any flow through CA.
There wouldn't be any flow through CS unless H2 is more than H3. Do you see that possibility? So how should we generalize our equation? So we're looking for a mathematical way of capturing this information. What information? This information that only there would be fluid leaving the first tank if H1 is more than H3 and H2 at the same time should not be more than H3. If the reverse happens, then we have to consider the relative level of H1 and H2. So I'll give you 30 seconds. Please think about it. How can we mathematically capture that? So to just help you a little bit and also help myself a little bit, you're looking for a math function that receives both h1 and h2 as well as value of h3, right? And what comes out of it should give us the net flow and also the sign of it. So if h1 is more than h3, it should give you a positive flow out. If h1 is less than h3, what should it give you? It should give you 0. Has no flow happening, right? And at the same time, if h2 is less than h3, it should give you 0. So that doesn't cause any fluid. But if h2 is more than h3, it should give you the reverse flow happening. So that's what we are looking for. Okay? So think about it. I'm going to keep it as a challenge. So let me write this down. Challenge question. How to generalize equation 1, where this is equation 1, and you know what I mean, how to generalize it mathematically. Of course, we can build into it if-then type expression. So if h1 is more than h3, this equation. If h1 is less than h3, that equation. If h2 is more than h3, the other equation. But ideally, we want to capture it with math. So some sort of function, absolute value, sine function, saturation function. So there are multiple functions that are nonlinear, by the way, and should be able to help us. So I'll think about it and we'll discuss it next time. Okay, so let's move on. Do you guys want a break? No? Okay, so let's look at another example. So we're going back to motion and mechanical systems. What I'm showing you is a system that has an inertia, mass m. It has an energy storage element, which is the spring, and an energy loss element, which is the friction. And what we want is to capture how this inertial element, how this mass moves. So we want to capture its displacement, which means in modeling language, it means I need a model. I need a differential equation that describes the motion of this system. So where do we start? When we have a mechanical system and we're dealing with motion, we always start from the free body diagram of the system, which we have here. So we have the free body diagram of the system right here. You can see the inertial element. You can see the applied force to the inertial element. So this is the external force that pulls down this mass. Variable y captures how much the mass moves from its equilibrium. What is the equilibrium? The equilibrium means if there is no force, where would this mass stop? So the effect of weight on the spring basically is captured through equilibrium. So if the spring is unstretched and you attach this mass, there will be an initial stretch because the weight will cause some elongation in the spring, some stretch in the spring. So y is measured from equilibrium. Please write that down. So y from what we call a static equilibrium. So equilibrium. So y is measured from that point. So when y is 0, the spring is already stretched and it cancels the effect of weight. So it's just there. It's not moving anywhere under the effect of the weight. Okay. So as I said, RT is a force that is externally applied. The externally applied force. And there are two forces that would oppose this downward motion. So under the effect of this force downward, the mass would like to move downward, but two forces would stop that motion. And these two forces are the force of a spring and also friction that opposes any motion, including the downward motion. So in our free body diagram, we are capturing those two forces. One of them, which is the force on the left, is the force of the spring. Now, force of a spring is proportional to how much the spring is stretched or compressed. As it moves down, the spring is stretched. So if you look at this plot, this is force of spring. This is y. And the slope is k, stiffness of the spring. So the spring is a linear element. And by the way, this plot continues to the negative sign that captures the compression of a spring. A lot of springs can be compressed, some of them can't. But if a spring can be compressed, it will create an opposite direction force, which is in the negative direction. So k times y captures the behavior of a spring. Now, modeling friction is not as straightforward. Friction, generally speaking, is a complex process, but there is a simple way of capturing spring is by assuming the force, opposing force of a spring is like a drag force. So the faster the mass moves, the more friction force would be. So we are saying the friction force, like the force of spring, is proportional, but not proportional to how much it moves. It's proportional to how fast it moves. So again, if you want to plot this force of friction is proportional. It's a linear behavior, but it's proportional to y dot, which is the speed. So that's our assumption. By the way, this is called a viscous type friction. That's the name of the model. And you've seen Coulomb type friction, where you have one constant level of force in static and another constant level of force when motion starts happening. But in this example, we are going to consider friction to be a viscous type friction. Okay, so we have the free body diagram. So this is our free body diagram that includes all the external forces. We have the force that pulls it down, pulls the mass down, and we have the force of the spring and the force caused by friction. Any other force that we need to include? How about the weight? Isn't the weight a downward force? It is. It is a downward force, but why is it not included here? There are two options. One, you made a mistake. Two, because we are measuring y from static equilibrium. What does static equilibrium mean? It means the initial stretch of the spring is canceled by the effect of the weight. So essentially, when y is 0, the spring is already stretched. By how much? Enough to cancel the effect of the weight. Okay, so where do we start to get to our equation? What is the law? It's mechanical motion. The law of physics that we are going to use is Newton's second law. It says what? Says m times acceleration, m times acceleration is equal to all the forces applied. Now, the assumption we have is that this mass only moves in the y direction. So the acceleration, therefore, would be also in the y direction. What is the acceleration in y direction? The acceleration in y direction simply is y dot or double dot. Y double dot. Y is displacement, y dot is velocity, y double dot is acceleration. So my double dot is equal to what? What forces are applied that we need to add up? We have RT. So let me write it down. So we have RT. What else do we have? Which is what? KY. And the damper force, which is Y dot. by dot. Okay. So in order to add, I need to know how to add. Are they positive or negative? Which one is positive? Which one is negative? Okay. So why do you call RT positive while it's downward, and the other one are upward?
The direction of y is downward.
Because that's excellent point. Because when we drew the free body diagram, we assumed this is y positive. That's the meaning of that arrow with the motion variable. So we're saying this is the positive direction. So anything, including forces that happens in the positive direction, would be treated as positive. Anything in the opposite direction would be treated as negative. So bear that in mind. So RT positive, the other two is negative. So what do we do next? We try to rearrange them so all the variables that include the terms that include y and its derivative would be on one side. So we have my double dot plus by dot plus ky equals RT. So what kind of equation is this? This is a differential equation. It's a differential equation. What is the order of this differential equation? It is order 2. Why do you call it 2? Because the highest time derivative is 2. So this is a second order differential equation modeling a second order system. That tells you how many state variables are there? Two state variables, because this is a second order system modeled by a second order differential equation. Now, what is the input to this system? R of t, basically. We chose R, but the force. The force is what causes this system to move. So the input is, does it say force F here? It should say RT. So this needs a correction. So that's the input. Now, state variables are position and velocity. Position and velocity. But how do you know? Can you simply look at the equation and decide what are the state variables? Let's remember. Let's remember when we had a first order system. When we had a first order system, what was the model? The model was this: t x dot plus x was u divided by p, right? And we said x was the state variable, didn't we? One way to know what is state variable is to look at your differential equation and see which variable is being time differentiated. In the first order system, the only variable that is time differentiated is what? X. So that's your state variable. Now look at this second order differential equation. What variable or variables are time differentiated here? Y and y dot. Y is time differentiated and you have y dot. Y dot is time differentiated and that's why you have y double dot. That's why y and y dot are your state variables. Please take a note of that. That's very important because a lot of times we get confused. What are the state variables? One easy way, if you have the model, of course, if you have the model, one easy way to distinguish and recognize state variables is, of course, you look at the order of your system and you see, okay, it's of order 2, so I need to have 2 state variables. But what are those? Look at variables that are time differentiated. In this case, y is time differentiated. That's why you have y dot, and also y dot is time differentiated. That's why you have y double dot. So y and y dot are both state variables. Now, how about output? Is displacement your output? Is velocity your output? Or both are your outputs? How do you decide? I've been repeating one word, and that word was the purpose of the model. Why are you doing modeling? What is your interest? That defines your output. Are you interested in tracking the position of the system? Then position is your output. Are you interested to know how fast this moves? Then velocity is your output. If you're interested in knowing both, they're both your output. So you have a state vector essentially here. So again, we have a state vector. Let me write it down. State vector is made of, now because I don't have room vertically, I'm going to write this horizontally, but put a little t to say this should be transposed. So it's really a column vector, but I don't have enough space, so I'm writing it as a row vector, but it's a transpose. Does this t mean anything to you? Means row and column would change places, basically. Okay, anything else? So here's your question, here's your challenge. If I give you this a constant input, if I give this a constant input, how will the output look like? Let's say output is the displacement. What will happen to the mass? How will the displacement change over time if I just give it a constant input? Constant input means like attaching another constant mass to it and let it go. That's equal to constant input, constant level of force. What will happen to this mass? It probably moves downward, but can you sketch the response? So can you sketch the response? How will it look like? Some of you have superpower. You're sketching without your pen touching paper, so I admire you. But give it the traditional try. Do it the traditional way. Grab your pencil, put it on paper, and plot the response. So if RT is constant, let's say 1, how will the response look like? So if this is T and this is Y. First of all, can you calculate steady state Y? What is Y steady state? What is Y steady state?
Force divided by your spring constant.
We know what the force is. It's 1. So what is Y steady state?
1 over K.
How did you get that?
Because the spring constant is the force over Y. And then just solve for Y. And since we know that our force is 1, just put in 1 for the force.
Okay. But what happened to your my double dot and your by dot?
That's a good question.
That equals 0.
Why?
That's what we did in the previous example.
Why?
Steady state.
Steady state. Steady state, it's built into it. Steady state means when will Y be constant, not changing with time anymore. That's when. We call that instant steady state, and at that instant and onward, Y dot is 0, no velocity. That's the meaning of a mass being motionless, means its velocity is 0. And so is its acceleration, because if acceleration is not 0, even though velocity is 0, it will change. So both velocity and acceleration and any higher derivative of Y, they have to all be equal to 0 in order for that point to be a steady state. So if you set Y double dot equal to 0 and Y dot equal to 0, the only equation that you're left with is Ky is equal to RT. Now if RT is 1, your Y steady state is 1 over K. If RT is 2, Your y state is 2 over k. Do you see that? So you gave me the correct answer, but we want to approach it from the differential equation. Why is it from the differential equation? Okay, so we know that this system will settle at 1 over k. So that's what we know. So we know that at the end, the system would be at 1 over k value for y. But we want to know how will it reach 1 over k. Let's say at time 0, let's assume at time 0, y of 0 is 0, and so is y dot of 0. So both position and velocity at time 0 are 0. So we know what is the status at 0, and we know if we wait long enough for the system to reach steady state, it will also reach 1 over k. So what will happen in the interim, in the intermediate step? Does anyone have any sketch? How does it look like? Yes.
Will it overshoot the steady state and kind of?
So what you're saying, this would start from here, yes?
Yeah.
And then go up. Oh, I deselected this. So it starts from here. And go up. And then does this.
Yeah.
Like that. But this also needs to be, right? Is that what you mean? Okay. Any objection? Do you guys agree that this could happen? So the mass could just overshoot and vibrate and essentially settle at a new equilibrium. This is, by the way, a new equilibrium. Didn't we say the equilibrium is when the weight basically offset by the force of a spring? Again, this happens. Now we have a different level of weight. It finds a new equilibrium. Okay? But let me ask you this. I was hoping that somebody would say, this system will behave like this. Essentially, behaves like the same way the first order system behaved. Is it possible that this system does not overshoot? Yes. If it is overdamped, or there is another one, critically damped, right? So it could also show that behavior. And we'll talk more about this. So what I wanted to bring to your attention is that a second order system has a more diverse type behavior. If a first order system only showed exponential rise or decay, a second order system has a wider range of possibilities, offers a wider range of possibilities. Okay, let's move on. Look at another example. You recall that if we are modeling a circuit with main analog components, we talk about resistors, capacitors, and inductors, and two main laws. The first law is the current law. Basically says conservation of electric charge. So if you have a node, the sum of currents coming in is equal to sum of currents going out. That's law 1. The voltage law, or second law, is conservation of electric energy. Basically says if you go around a closed circuit, you add voltages, they would add up to be zero. So you're not generating in the circuit itself or losing energy. It's just conservative. So what comes in basically is consumed. Okay, so we're going to look at this example. So I'll give you 30 seconds and to come up with the model, or at least get to the law that you want to use. This circuit has a source of current, RT, so we can control how much current we put to the circuit, and all the three elements are in parallel, so voltage across them are equal. So we could define the purpose of modeling to relate how the current R is going to affect the voltage V, which you can read at the two ends of any of these three elements, at the terminal of any of these three elements. So let's choose our output to be the voltage. That's the purpose. So the purpose of modeling is to relate the effect of input current to an output voltage. So apply your Kirchhoff's law and see if you can get to the equation. So how will you get to your to the equation for this circuit? We probably all agree that if there is a current that comes through from this source of current, it will be split in here once and split again here. So you have different currents passing through these three elements. So if we call the current passing here as I1, current passing through here as I2, and this as I3, what can we write as the relationship between I1, I2, I3, and R, which is the source of current? What is the relationship that we can write? How do we know that? Look at each of these nodes. If we call this node A and call this node B, at node A, what we can write is R is equal to I1 and what goes through the conductor between A and B. Now, what the conductor between A and B carries I2 and I3 both. So what we can write is this. R of t is equal to I1 plus I2 plus I3. Now, what is I1? It's current passing through the resistor. But what is that current? What is the relationship that we can write between that current and the voltage across? What can we write? I1 is equal to V over R. When V is the voltage that we read across those two terminals. How about I2? What do we know about I2? What is the basic equation of an inductance element? The basic equation for an inductance element is that its voltage is equal to L times the derivative of its current. Now here we are after the current, which means we have to use the integral form of this equation, which means I2 is plus, so this is the plus from the top, so plus 1 over L integral of V dt, that's I2. And what is the current passing through a capacitor? According to the basic equations that I showed you on the previous slide. Again, let's go up and take a look. The basic equation of a capacitor is that its current is equal to its capacitance C times the derivative of voltage. And that's what we want. So we have plus dV over dt. So all these three added up is equal to RT, which is the input current. So that's our basic equation. So we are relating our input R to our output voltage through that equation. Now, if you want to arrive at a purely differential equation with no integration, you have to do what? You have to differentiate it, time differentiate it. If you time differentiate this equation, you get dr, or let me use dot so it's easier to write. So r dot t is equal to v dot over r plus 1 over lv plus c v. What will happen to dv over dt if I've differentiated? Becomes v double dot. Or you can rewrite it as cv double dot plus v dot divided by r plus v over l equals r dot t. Now look at this equation and compare it to what? compare it to the last equation that we had was what? It was m x double dot plus b x dot plus k x equals RT, which in that case was a force. So that tells you the same thing that we did for first order systems, where we modeled one physical system and then looked at other systems and said, okay, this has a similar model to our first system, therefore it must behave the same way. The same exact analogy happens here. So even though we are talking about an electric system, its behavior very much would look like the behavior of a mass damper spring system. And before we had digital computers, by the way, guys, we had analog computers. Ever heard of analog computation? Analog computers basically was that we needed to simulate behavior of systems, but we didn't have digital computers. We didn't have microprocessors. So what they did, they would create circuits that would behave like a mechanical system. In a circuit, it's easy to apply current to measure voltage. So instead of making a mechanical system and let it vibrate, you make an electrical system and apply current and measure voltage, or apply voltage and measure current. So by recording changes in current and voltage, you effectively are simulating a totally different mechanical system, or a totally system. It could be mechanical, it could be fluid flow, it could be an economic system, you name it. So that was the basics of analog computing, by creating circuits that behaved similar to other physical systems. So this is your next example. Go ahead and find a model for this system, please. So this system is made of a source of voltage, a resistance, an inductance, and a capacitance. So which Kirchhoff law are you going to use? The current law or the voltage law? The voltage law. So you have a closed circuit, you go around the circuit, you add voltages, and they should add up to zero. So starting from the source of voltage, this is a positive V. The first element is the resistor, so its voltage drop would be I A times R. So I times R is the voltage drop in the resistor. How about the next element? What is the voltage drop there? What is the basic equation for an inductor?
L times the derivative of the current.
So it's minus L, and the current is the same because it's a series connection, so all of these elements would see the same current, all three elements. So the current generated by that source goes and doesn't change because we don't have any branching. Okay, and how about the last element? What is the current there?
1/c times the interval.
So the basic equation for a capacitor is an equation for the current. So when we need the voltage, we have to turn it around. So it would be minus 1/c integral of I a dt, and that is all equal to 0. Again, the standard approach is to differentiate, so we arrive at a purely differential equation. So we have L, second derivative of I with respect to time, plus R, first derivative of I with respect to time, plus 1/c IA equals V, let's use the same type of notation, d/dt of V. Now compare that to M M x double dot plus B x dot plus K x equals force So you can see that in this circuit, the inductance work like an inertia element. The resistor works like friction. It's a dissipation element. And the capacitor works like a spring. It stores energy and releases energy. Can you see that? Yes.
Does voltage change over time?
The voltage could change over time, yeah. So in general, the input to the system changes. So you can basically have either AC or a variable DC source, yeah? Could change over time. Did you have a question?
No, it's just
Okay, here's your next problem. So we have a mechanical system that is made of 3 energy storing elements. Call it spring, but they don't have to physically be a spring. A tire has the same effect. The polymer in the tire, when it receives load, deforms, stores energy, and releases energy. We also have an energy dissipation element, either intentionally, like a dashpot, like a damper, or the fact that any mechanical element is not an ideal energy storage and energy release. And every time you put energy into a tire, it doesn't release it all back. So we have some dissipation. So we have to capture that loss of energy somehow. And what we are doing is we are capturing it as a damper, as a viscous damper. So there is a source of displacement, which would be the roughness of the road. So the displacement, the source of displacement change is shown here with this double arrow. So it could basically get closer or gets farther away. We have one stiffness element, one energy storage element. Again, this could be the tire. This is the energy dissipation that happens through the tire. Then this is the actual spring. And this is the deflection of the chassis itself. So we have the deflection of the sprung mass, the unsprung mass. So we are basically capturing the behavior of this physical system, or a corner of this physical system, we should say, 1/4 of this this car go-kart with this model. So 3 energy storage element, 3 springs, K1, K2, K3, an energy dissipation element with as a viscous element B with constant B. Input, we call this U of t as input to the system. Q1 basically captures how much displacement mass 1 sees. Q2 rather sees how much displacement mass 2 undergoes. So we want to get to, the first step is to draw free body diagrams, and we have to have 2 of them. Each inertial element has its own free body diagram. And once we have one free body diagram, we can go ahead and write Newton's second law for that free body diagram. So I'll give you a minute to get started, and then we'll work together on it. So mass 1 and mass 2. So let's start with mass 1. If Q1 captures the net deflection of mass 1 from its equilibrium position, so from equilibrium position, Q1 captures displacement of mass 1, and to the right, Q1 to the right is positive. So this is Q1 displacement. If that is the case, we'll have a resistive force from the first spring. That would be K1 Q1. That's the net force. And depending on how much the second mass moves, either this spring K2 would be stretched or compressed. So depending on the relative value between Q1 and Q2, we will either have the spring stretch or compressed. And both are possibilities, and both will happen as these 2 masses move. But we need to make an assumption for now and stick to that assumption so we can write the equation. So if we assume that, so this is Q2, and let's assume that at this instant in time, Q2 is larger than Q1. If we make that assumption, we are basically saying that the spring would be stretched. So if that is the case, then we have the force applied on mass 2 by the second spring this way. So that's K2, Q2 minus Q1. And the direction on the second mass would be opposing, in the opposite direction. But the amount of force would be the same. That's all for mass 1. For mass 2, we have, of course, the force coming from K2, but we also have the force coming from K3. And the assumption we are going to make is that U, the input, is larger than Q2. So we are going to assume that U of t is larger than Q2, which means the force applied by the third spring is to the right. So it's K3 U minus Q2. 2. So K3 U minus Q2, close parenthesis. And then we have the force of damper also. The force of damper would also oppose the motion of Q2, which is to the right. So force of damper would oppose that. So it would be in the opposite direction. If I can draw it somewhere here. If not, I'm going to draw it here. This is B times Q2 dot. The damper force is proportional to the velocity. And you can see that the assumption we are making is that the damper on one side moves. The damper on one side moves, but on the other side, it doesn't. So the damper on one side is stationary and the other side moves. So the only moving side is what is attached to M2, which is shown with variable Q2. So velocity of the second mass defines that force. Are we missing any other force? Or are we ready to write Newton's second law? Or do you have any questions about the forces, the directions? Okay. So let's go ahead and write Newton's second law for mass 1. So for mass 1, we have m1. What is the acceleration of the first mass? What variable shows the acceleration? q1 double dot, right? So q1 double dot is the acceleration of the first mass, and it is equal to, so we have the first force in negative direction, minus k1 q1. The second force in positive direction is plus k2 times q2 minus q1. That's for this, the first mass. For the second mass, we have m2 q2 double dot. That's its acceleration is equal to. Now let's start from the first force, which is negative force, minus k2 q2 minus q1. Then we have another negative force, minus bq2 dot. And then we have the third force, which is plus k3 u minus q2. q2 u minus q2, close parenthesis. So we have two second-order differential equations. We can rewrite them to have the more of the standard appearance. So for the first one, we'll have m1 q1 double dot plus what? Plus k1 plus k2 times q1, and that is equal to k2 q2. That's the closer to the standard form. And let's go to the second equation. We can write it as m2 q2 double dot plus bq2 dot plus, what is multiplied by q2? We have k2 and we have k3. So plus k2 plus k3, close parenthesis, times q2. And that is equal to, what is left? We have k2 q1. So we have k2 q1 plus, what else is left? K2 q1 is left, plus plus k3 times u. Yes.
Where did you get Q1 dot for the first equation?
I didn't. I just made a mistake, didn't I? So there should be no dot in the first equation. Let's see if I can just remove the dot. Okay. All right. So let's answer this question. What is the order of this system? It's second for each of these two equations. So what is the order of this system? Just to refresh your memory, let's go back to the first example that we solved. What was the order of this system? We had two first order differential equations. We call this as a second order system, and it had two state variables. Now let's fast forward. This system has two second order differential equations. So it's a fourth order system, and it has four state variables. And the state variables are position and velocities of each of the two masses. Okay, I'll stop here. Thank you.